Good morning, everybody. I don't think anybody should be able to. Let me share the live page. Please share the YouTube. Please share. Okay. 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 Good morning. This is my name, Dr. Mrs. Ooloba Whenu. You can address me as Dr. Whenu. I'll be teaching you thermochemistry, thermodynamics generally. It's the first law, and then we'll talk about the second law in the second week. Let me see if people, okay, I think I've been able to go live. Please, you can ask questions during the course of the lecture. Just type in your questions as we go along. Please don't type in anything that is not useful because I'm reading the chat as we go along. So if you type meaningless messages, you're going to delay the class rather. All right. And for those on YouTube too, I'm also trying to look at what you're typing as well. So please, let's try to minimize what we say. You can write your names and matric number for later purpose, but other than that, somebody says that they can't hear me. Guys, okay, I'm on the YouTube link. I have shared it. I think those of you that can't hear me, it's probably due to your connection. It looks like a lot of people can hear me. There are not many people complaining. Can you hear me, please? Just answer in the chat. YouTube too, you can answer or show some sign that you can hear me. All right, so let's start. Okay, I've seen that you can hear me. All right, thank you. So let's start. If you can't hear me, please check your connection. Okay, so again, I'm Dr. Whenu. We're going to be going, I'm going to teach you thermochemistry that involves the first law of thermodynamics, and then we're going to talk about a little bit about the second and the third law of thermodynamics that talks about how reactions go in the directions of reaction. The first law talks about conservation of energy mostly and energy content of systems. So without much further ado, let's move on. YouTube sets and then, okay, so I'll probably update this in the one that I will share with you so that it's slightly bigger. So this is the outline of thermochemistry. We're going to look at basic concepts, the nature of energy, thermodynamics, first law of thermodynamics, enthalpies of formation, bond enthalpies, and food and raw. So bond enthalpies are ways to calculate enthalpies of formation as well. But like with everything, we need to create a premise and define some important things. One basic definition, one basic concept that you would always come across in thermodynamics. There's a picture at the back. There's also a picture here. There's a picture in the background, system surrounding boundaries, surrounding systems. So that's the recurring theme. So a system is the part. So the totality of everything that you can think about is called the universe. Now, the part of the universe that's being studied is called the system. Is a specific part of the universe that is being studied. So for those of us in chemistry mostly, the system is often probably a test tube like or a conical flask like the one drawn here, which contains a solution of anything. In this case, it contains a solution of barium hydroxide and ammonium nitrate. So that is the system that we are dealing with. Every other thing around it is called the surrounding. Both the surrounding, the system, they make up what we call the universe. So the surroundings, the air around it, the air around the flask, and it is separated, the system and the surrounding are separated by what we call a boundary. So the nature of the boundary determines the kind of systems that you're working with. So those of us in engineering, you're probably working on an engine. Whatever is inside the engine is your system. Those of us in medical sciences or plant sciences, whatever you're working on is your system. The system may be open, closed, or isolated. An open system allows you to exchange matter and energy with its surroundings. So remember, we said the system is what you're dealing with. So this is an example of an open system right at this corner here. So somebody is cooking some kind of delicacy that the person wants to eat. So what the system is, the pot is the soup that the person is cooking. As steam is getting out, matter is going out. Matter is something that occupies mass, occupies space and adds mass. So an open system allows you to exchange both matter and energy. So there's energy supplied to the pot, to the system that's cooking. And as the steam is going out, energy goes out with the steam. Matter is also going out. You can also have the closed system. That's the usual or the common one that we come across in almost everything that we do. So a closed system allows you to exchange energy with its surroundings, but matter is often not allowed. Okay, so I said that a closed system is the most common in experiments. In real life, the open system is the most common. So this is an example of a closed system. So like a cartoon drawing. So you have your sample in a vessel. The vessel is covered by a movable piston or a movable container cover, such that if your reaction is taking place, that piston can move up and down. So you are allowed to exchange energy by moving the piston. You exchange energy with your immediate surrounding. However, whatever is inside your container is not allowed to leave that place. So the people in in environmental science or in plant-based studies, they try to create a pseudo closed system, but calling it a greenhouse. So in a greenhouse, you try to contain everything that you have, but you minimize whatever matter goes in and out, such that it's only energy that's exchanged between the greenhouse and the system and its surrounding. The isolated system, that's the third one that you can also have. Now, that does not allow you to exchange energy, neither does it allow you to exchange matter with its surrounding. So those of us that like to cook at home and go and buy our gases, if you do not open the valve, your gas is isolated in the system. And if you put it at the right temperature, um, there's no exchange of temperature. If it's well insulated, there's no exchange of temperature between the system and its immediate environment. So isolated systems, the whole universe in itself is an isolated system. So when I'm saying the whole universe, I'm not talking about just the Earth, I'm talking about everything that has been defined to be contained in the whole universe, galaxies and all what's not. So it in itself is an isolated system, and that's the way it has been defined in thermodynamics. So moving on, so we said that energy is a what is energy? So moving on to in our definitions, energy is the capability to do work or transfer heat, and it can occur in different forms: mechanical, chemical. So the word thermodynamics, which is the umbrella under which thermochemistry falls on, is the study of energy as it changes from one form to another. This is supposed to be my first slide. I don't know how I managed to mix it up. So thermochemistry is a branch of thermodynamics that focuses on energy changes that accompanies chemical processes and physical changes. Our learning goal for this topic is to understand how energy is related in making and breaking chemical bonds. Like I said, this is supposed to be my first slide, but that's it. So I said we said that there's so many forms of energy. So there's chemical energy. This is the matches that we use at home. The substance that is in most matches that we come across is I think it's pink phosphorus. So you strike it, you create a reaction, and then you have combustion. Energy is released during that. So you have a chemical energy present there. You have radiant energy, that's energy transmitted through space in form of electromagnetic waves. That's the one that we use to power our solar panels nowadays. Another radiant energy that we commonly use is the one inside our microwaves. It's a form of electromagnetic wave. Electrical energy, well, we switch on and off everything. So nuclear energy stored in the nucleus of an atom. So how is nuclear energy different from chemical energy? Chemical energy is stored in bonds. Nuclear energy is stored in the nucleus. Then you have thermal energy as a result of motion. Again, so these are all several forms of energy that can be interconverted from one form to another. They fall under two categories generally. Whichever way you want to look at energy, it falls under two general categories: the kinetic energy and the potential energy. So the kinetic energy, that's the energy as a result of motion. Excuse me. Anytime an object is in motion, it possesses some form of kinetic energy. And we have the formula C equals half mv squared. So one of the ways to represent kinetic energy, mostly in classical mechanics in physics, is the symbol T. Of course, you can also have it in your other textbooks as Ke. What is important is to make sure that it is being defined as kinetic energy and not temperature. When you are referring to, when you talk about X, you need to express what your variable or your dummy variable stands for. So our T here stands for kinetic energy and is given the formula half mv squared, where m is mass and the small v that we have written here is velocity. So an object with a higher mass and moving at a greater speed will definitely have higher kinetic energy. So in chemistry, the kinetic energy comes from motion of particles. particles are always in motion. The most important one is our electrons flowing through the bonds, and it is constantly in motion. Electrons have their mass, and it's not just one of them. So that's where the kinetic energy comes from. Another form that where we can associate our kinetic energy is that it results in thermal energy, because the faster a particle moves, it generates temperature as it's moving. So it's related to temperature, sorry. So the more you increase the temperature of a system, you increase the velocity of that particle. So your kinetic energy is associated with thermal energy. As a matter of fact, you can calculate interchangeably velocity of some particles. You can estimate temperature of the system once you know the velocity, and vice versa. If you know the temperature of a system, you can infer the speed at which that system is moving. The other form of energy that we said we can categorize them under two categories. The other one is potential energy. Potential energy is as a result of position. So whenever you're talking about potential energy, you're talking about the position of one object with respect to another. So the common one that we're familiar with is the gravitational potential. So you have your object on the surface of the Earth at a certain distance or a certain height from it. So that's the one that we call the gravitational potential energy. And it has the formula mgh. It is energy stored. So that's energy stored within a gravitational field. So potential energy is energy stored within a certain field in which you exist in. There are different fields. There's magnetic field. So if you have a magnetic object in a magnetic field, then you have a magnetic potential. And that also has its formula. It's I think it's a magnetic moment multiplied by the field strength of your magnetism. Now back to chemistry. In chemistry, the most important potential energy that we talk about is electrostatic potential. And why are we talking about electrostatic potential? Because particles in our systems are charged. And if they are charged, then there is an electric field that's generated. And if there's an electric field, that means that we're talking about an electric potential or electrostatic potential. So the electrostatic potential between charged particles is Q1 times Q2 divided by the distance between them, multiplied by a proportionality constant. So Q1 and Q2 are the amount of the charges on the two different charges that we are looking at, and D is the distance between them. So this measures the strength of the nearby charges and the nucleus. So let's write it properly. Electrostatic potential, so that we see where those charges come from. K is a proportionality constant that you do not have to memorize. Constants are often usually provided because you have a handbook that contains a standard values of several constants. So so one thing about charges. Let's do a little bit about physics of charges. When the charges are alike, they repel each other. And so this is a plot of electrostatic charge versus the distance between the charges. So this is the direction or separation between the two charges. If the charges are the same, whether they are both positive or they are both negative, at infinite separation, at infinite separation, the we're supposed to write attendance. Please write your name and your department and matric number. When the two charges are very, very far apart, they don't feel any form of repulsion or attraction towards each other. So the potential energy is zero. As they come closer, if if they are of the same type, that is, if they are both positive or negative, repulsion ensues between them. And if there's repulsion, it means that the potential energy it becomes positive and they repel each other. If it's attraction, the energy is stabilizing and it goes to more and it becomes negative. So the electrostatic is negative between two opposite charges and positive between two like charges. So there's attraction. So like charges repels, that's what I just described. And opposite charges attract. And electrostatic energy is negative. Okay. So what's under there is that potential energy becomes more negative as for like charges, potential energy decreases as they move apart. For unlike charges, potential energy decreases as they move closer to each other. In our chemical systems, where do we have charges? Giving an example of sodium chloride, giving an example of salt, common salts that we use at home, sodium chloride. Sodium is positively charged, chlorine is negatively charged. So you see, as they are far apart, they come together. So you have electrostatic potential within them. What about molecules? Please, this is not the place to be asking how are you doing. I only need your questions. That's all. In covalent bonds, molecules, that's where atoms share electrons. You know, in ionic bonds, you have a definite positive center and then in a negative center. For example, our sodium chloride here. This is chlorine and that's sodium. In a covalent molecule, for example, H2O. So we have bonds that are being shared. Are electrostatic potential still important? Yes, covalent bonds are also electrostatic in nature. How so? There are electrons between the bonds, and then if the unlike charge are infinitely apart, will they still have potential energy? I said it the other time that if the charges are very, very far apart, they don't feel anything because they are no longer in the field of that other one. I hope I've been able to answer that. So in both cases, both like when they are unlike charges coming far apart or like charges if they are far apart, as long as you are not in the field of that system, then you are not having any potential. If you want to bring it to the concept of gravitational potential, it is possible that a system or a particle, once it escapes the Earth's gravitational potential, then it does not have any potential field with the Earth, potential energy with the Earth. It has the potential energy with something else. All right, I think I've been able to answer it. Covalent bonds are still electrostatic in nature. Let's come back to class. And also because an atom is made up of a positive nucleus surrounded by negative electron clouds. So let me draw this. I think there's nothing coming here. So you have your positive nucleus surrounded by negative cloud, positive nucleus surrounded by negative electron cloud. So this electron cloud is still attracted by this positive nucleus. This electron cloud is attracted by this positive nucleus. So there's still an electrostatic interaction that is taking place within them. And one reason why you don't see, if there's an attraction between these electrons coming here, there is a repulsion between this electron cloud and this electron cloud. And that's why you don't see the whole system coming in or crashing together. Okay, so moving on. The units of energy that we are familiar with is joule. Another unit is calorie. Calorie was actually the original unit, but with time, the joule became more acceptable. However, for those of us in food industry, we still use calories a lot because calories can be more related to combustion. And more often than not, the calories that you see that are mentioned in foods are often determined by combustion. Okay, so let's work one or two examples. There are plenty of examples on the slides that you can play around with. So a person weighing 85 kgs runs the course at 187 meters per second. What's the kinetic energy in joules? Kinetic energy is half mv squared. We're given mass, we're given the speed. All we need to do is substitute our values, and then we arrive at the kinetic energy. So this is the kinetic energy in joules. This is, if you want to break down joules to the SI units, to the fundamental units, that's what you have. If you want to convert that to calories, I don't think in calories, from the equation on the slide. So this is copied directly from my notes. So from the equation on the slide, 1 kilocalorie is 4.18. That's in the previous slide. Is 4.18 kilocalorie. So you can easily remember how you do that. Do a cross multiple, and then you have your joules calories. So that would be 310. Sorry, so this 310 should be on this side. So 310 divided by 4.184 times 1. So that is 7.4 calorie. Yes, I will send the slides. But when I'm sending the slides, I'm not going to give you the solutions. So please pay attention in class. I'm going to send slides with questions, but you won't have solutions. You will have solved it in class. Any other questions there? Okay. Another one that's also straightforward, the potential energy of an automobile parked at the top level of a garage that's about 36.6 meters high. So this is a gravitational potential given by mga. So our mass is 13.1, wow, 1,360 kilograms. gravitational constant, and their height. So substituting gives that. Also, a straightforward example, and we calculate our potential energy to be 488.1 kilojoules. So for those in construction, all these things are put into consideration. Okay, so last example before we move on. Find the distance between 2 point charges, 0.1 and that respectively. So we know that our electrostatic potential energy is given by K times Q1 times Q2 over D. If electrostatic potential is, the question is talking about electrostatic potential, and we are to find distance. So this is the distance that we are to find. And from the question, we have been given different charges. This is the SI unit for charge, coulomb. Please write your name, even those of you on YouTube, write your name on YouTube. Final answer for what? Somebody else who saw the final answer on YouTube, please. I don't have slides for the topic. I'm going to share the slides after this class so that you can have it ready for the next class as well. Okay, so moving on. So we can make D subjects of the formula. So that's a top, making subject of formula. I'm sure it's just bring D to this side and EL to the other side. If you bring D here, it comes up. And if you bring EL there, it becomes the denominator down there. So we already have all these constant values or these values, so we can slot it into the equation. This is K constant, the charge 1 and charge 2, and this is the electrostatic potential given in the question. E electrostatic. Q1, Q2, K. It's always very interesting when people come late and get frustrated. What are we even doing? I don't know. What is the definition of electrostatic energy? I'm lost. Okay, so for the first question, so this, if you put all this in your calculator, you arrive at that. Any other serious question here? Oh, let's see. How do we know that G is 9.8? This person did not go to secondary school. Let me see any more question there. Will constant always be given? Me, if I don't always know constants, there's something that we need to always understand about constants. Constants are something that have been derived. They can be, you can get them in different units. So the number of constants that exist, I don't even know. So nobody expects you to memorize constants. If a constant is not given in your exam, you are allowed to ask. It's a valid question to ask in the exam of the constant. Can you explain question 1 and 2 again, ma? So that's calculating potential energy and kinetic energy. Abba, sorry, I want to answer question based on the first question and solution. You want to answer a question or you want to ask a question. If you want to ask your question, 0.599 meters. I'm not sure I'm following that. But is the negative sign necessary in solving? Is it that I did not put it? Yes, it is necessary now. Okay, general advice. I don't understand is not a question. Electrostatic potential is energy. So electrostatic potential energy is always in joules. Ajayi Obaloluwa. Is the negative sign necessary? Yes. Can we put answer in standard form? You can put answer in standard form, that's fine. Unless it states otherwise. Where did we square D now? Huh? I didn't square D. Am I supposed to square D? So why is the electrostatic potential here negative? It's between opposite charges. Yes, you will get lots of practice questions. So that reminds me, the book that I'm using is Chemistry, the Central Science. That's the one that I'm using, and that book has plenty questions at the back of it. I will share the picture with you. I will share the name with you on the WhatsApp book group, so you can have it with your friend. Okay. Man, the live chat on YouTube is live, is not on. Who told you that? I'm even reading it. Okay. So let me go back to the previous slide. So for those of you that were looking for the previous slide, oh, come on. 2 seconds. Use the app instead if you are using browser. Thank you, Anyofe Oluwa. So this is the copy. See, this is the live YouTube, I hope. The understanding one on question 1. So this is the first question. This is the second question. I don't know why I'm even going back. The questions are straightforward. K is a constant. Oh. There are some people that went to serious school. Oh. For those of you that are providing answers, thank you. Okay, I need to quickly talk about something because we have a lot to cover. Energy is the capacity to do work. What is work? Should we always convert to kilojoules? I think you should look at the question, look at your answer, look at what you have on ground. Work is energy The solving of the question one, the part yourself for final answer. There's something about how we express ourselves. So now, if you want to ask a question now, I'm sorry I'm diverting, but this is part of learning too. When you want to express yourself, please express yourself such that the person can understand you as much as possible. For example, somebody wants to ask me a question. I think I don't understand. The solving of question one, the parts you solve for final answer. There is no way I can understand that. And the reason I'm going back to it is not because I want to waste time. When you say, okay, you are in year one now, probably most of your questions will be objective. When you move to higher levels, what you will be encountering is for you to be writing down. So you see, most people fail in their exams simply because they cannot express themselves properly. And you come out of the exam, you will be like, I solved it very well. You might have assumed something. The fact that I'm your lecturer does not mean I don't want you to express yourself as much as possible. So put that into consideration. There's no way I can understand your question. There's no way I can answer you if you don't express your questions properly. Okay, let me quickly finish this slide and then we'll call it this, I think work and eat. Work is energy that causes an object that you use to make an object move a certain distance against a force. So work is the best way it's written is force times distance. There's another question here. When the charges are repelling, should okay, so the general answer on that, like I showed before, when you have two charges that are of the same sign, it can be both positive or both negative. The electrostatic potential is positive. I showed a slide and I showed a plot to show to indicate that. When you have them that are of opposite charges, negative, positive, positive, negative, then your electrostatic potential will be negative, Q1 times Q2. So the most common work that we encounter in chemistry is pressure volume work. So pressure volume, so work can be different in different forms. You can have surface tension work, you can have electrical work, and they all have their distance. You are moving an object through a certain distance and against force. So that should be actually minus F times FD. So the most common type of work that we encounter is pressure volume work. So pressure is the force. Volume, you're expanding your gas through that distance. So that's a certain distance that you are working through. So it's a form. So in such a cases, we are saying that gases that are undergoing expansion are doing mechanical work. So I've put negative sign here, minus P delta V, because I'm defining work from the perspective of the system. Are you serious? Some questions use 9.8, some use 10. Oh gosh. I was trying to ask, the first question you thought in the first solution, can you please explain again? So, okay, Olashubumi, I can assure you that you have still not expressed yourself properly. 4 more minutes. The negative sign shows that the system is doing work. That's what I'm trying to say. So you have your system is doing work on the surrounding. So this is our system. Work is going from the system to the surrounding. So we define it as negative W. So that's why you have this negative sign. Delta V is change in volume. You can express it as V final minus V initial. And some other text that you can pick up, you may have V2 minus V1, meaning that you are going from an initial state 1 to a final state 2. P is the external pressure that's acting on the system or that you are working against. In electrochemistry, we talk about electrical work. Last slide that I will talk about today, heat. Is minus necessary when? So is it necessary to always say it that way? So is it necessary to include the minus? So let's say it again. So work is energy done by the system. So if it's energy done by the system, it is defined as negative P delta V. So it's possible if work is done on the system, yes. Will the work be positive? Yes. So we'll quickly look at find converters. I think that we won't be able to get that for that. So let me talk quickly about heat. Remember, energy is capacity to do work or transfer it. I apologize for my beautiful handwriting. So it is energy that causes a change in temperature of the system. So it is energy that flows in and out of a system due to temperature difference in the system. Again, Q is defined from a negative perspective. So meaning that if the system loses heat, Q is negative. If the system gains heat, Q is positive. So it often flows from a region of higher temperature to a region of lower temperature. And once the temperatures are equal, it stops. Work and heat are forms of energy. I also saw D squared. Don't worry, you will get the slide and you use the slide before the next class. So I have a feeling that you have another class now. Unless you don't have another class, I can go on to the next slide. Any question before we call it a class today? We're going to move faster than this. No more question. Electrostatic potential energy. When will work be positive? Work will be positive when you do work on the system. So positive work will be compression. You can go to your other class. I'm just looking if some people have questions. That's okay. I don't think there are any more questions, so I can end the class. Okay, so the last class we had, I didn't get the slide, the one about how different scientists. So in a situation where you don't get a slide, please tell there's a Telegram group. You can say that you can make your complaints there. The other one, if you are the class rep, please request for it on the platform where class reps are with the lecturers. If you're not the class rep, please tell your class rep. You have a class group. Tell your class reps to do that for you on your behalf. Please explain if the system gains or loses it. Don't worry, I'll shed more light on that next class. There's a slide that's dedicated on gaining and losing it. Let me see. Intuitive question. When heat flow stops, does that mean system transfer of energy has stopped? Not necessarily. There's something called equilibrium. There's a continuous flow, it's just equal. So I'll share the textbook, the name of the textbook. I'll share it on the platform. Okay, for those of you that don't understand the concept, the negative and the sign, there's a slide dedicated to it. We didn't get to it today, so we'll get to it next class. All right, it's 10 o'clock. You said you have another class. You are still here. I'll see you all next class.